Welcome back. In the previous class, we started to talk about the condition under which an ultra thin film can spontaneously become unstable with the formation of holes due to the attractive interfacial interaction between its two interfaces. So, the essential concepts that we discussed, that a liquid film surface irrespective of its thickness has some very tiny fluctuations even if it is completely stagnant, and it is isothermal. So, there is no temperature gradient, there is no evaporation, there is no external pressure from outside. So, in a situation like this, irrespective of whether you are talking about a film or you are talking about a pool of liquid or a tank or a bucket of water or a liquid, any liquid, it really does not matter. Macroscopically, such a system will offer a completely flat interface or the top surface, and when we investigate, so this we all know. So, what it implies that the velocity components of velocity u, v and w at every location within the flow field will be uniformly 0, which implies that the top surface of such a liquid layer will be completely flat. Okay. So, this is a perfectly valid, we argued that this is a perfectly valid picture of the interface if you are talking about macroscopic length scale, but when we investigate the same interface at a sub 10 nanometer resolution, let us say, we find that there are some very tiny fluctuations which are present on the surface of the liquid, the origin of which is attributed to the thermal energy of the molecules, which is omnipresent or always present, because they scale as kT, and if you are performing your experiments or you are operating at a temperature which is not at absolute 0, then this component of energy you can never sort of eliminate, and you can also have some mechanical vibrations. So, consequently, there are these very tiny little high frequency low amplitude oscillations which are always present on the surface of the interface, and typically the moment these fluctuations sets in, surface tension opposes these growth of these fluctuations. So, you have a dynamic equilibrium prevailing on the surface of the film. So, essential features are, this is triggered by the thermal fluctuation and which is opposed by the restoring effect of surface tension, and these fluctuations also give rise to a non-planar liquid surface. So, there are localized or spatial variation of Laplace pressure along the surface of the film, and which results in flow of liquid from these zones, the zones with where the sort of the peaks of the fluctuating surface to the valleys of the fluctuating surface, restoring the film back to its original flat morphology. So, this we understood to its flat morphology. Now, in a macroscopic situation, these tiny fluctuations have no significant implication because of the fact that these have typical amplitude of the order of couple of nanometer. So, in the macroscopic length scale, even if a layer of liquid is couple of centimeter thick, these are very insignificant. And there is also, these fluctuations are provided by this thermal energy of the molecules, but there is no additional scenario or additional driving force for amplification of these oscillations. The situation sort of changes when we now start talking about a thin film, and we identify a thin film as a system. This we have already talked several times, where there is active interfacial interaction between the two interfaces. So, here you have a film which, let us say, is coated on a rigid substrate, and so this is the substrate, this is the thin film. Since we use the word thin film, so it implies that there is active interfacial interaction between the two interfaces. That is the film air, or the, in case it is a liquid film, it is the liquid air interface, and the liquid solid interface. Okay. So, there is an active interaction between these two interfaces, and these interaction can be either attractive or repulsive. Then we argued that if there is, we considered individually the two cases where you have individual attractive and repulsive interaction. So, we saw in a situation where you have a repulsive interaction, what happens is this area or the valley of any instantaneous surface fluctuation, which is actually closer to the or this is a location where the two interfaces are closer to each other. Now, since there is an active interaction between the two, over here the repulsion now is stronger as compared to the repulsion in this particular zone. Therefore, the repulsive interaction augments with the stabilizing influence of surface tension. So, the repulsive interaction sort of augments with the stabilizing influence of surface tension, and the film remains unconditionally stable or intact. I will just add the word unconditionally stable. Okay. So, this is what happens if you have a very thin film with a interfacial interaction which is repulsive in nature. In contrast, if you have a scenario where the interaction is now attractive, then what happens is that over this zone, a zone which is which corresponds to a valley of any instantaneous fluctuation, the two interfaces are now closer closer over here as compared to a valley, a peak of the surface fluctuation. Let us say this is H 0, this is my mean film thickness. So, therefore, what happens now, the interaction now which is attractive, the interaction or the attraction is stronger here. As compared to the other zones. So, now the two forces or two force fields, that is the interfacial interaction and surface tension, have antagonistic or opposite roles. So, these are the two antagonistic influences now. While surface tension even now tries to stabilize the film, the attractive interfacial interaction now tries to destabilize the film in way of trying to amplify the surface fluctuation or trying to enhance the amplitude surface fluctuations. Okay. And in the event that this attractive interaction sort of becomes stronger than the strength of the attractive interfacial interaction becomes stronger than the restoring effect of surface tension, then what happens is that eventually these tiny surface fluctuations grow in amplitude, and progressively their amplitude grows, and when the amplitude of the film matches the growing amplitude of the film matches the film thickness, the film has ruptured. What it means that the amplitude of the film matches the film thickness, essentially the two distinct interfaces, that is the film air and the film substrate interfaces now merge with each other to form a 3 phase contact line around the hole. Now, there is some additional subsequent dynamics. So, what happens is that what the scenario is like this. Now, all you have done is that you have taken a film on a substrate, and simply based on the interfacial interaction, the strength of the attractive interfacial interaction, now this film has ruptured, forming a hole. Now, there is no specific reason if the surface is defect free, there is no preferential spot where a hole should nucleate. There is no reason to assume that only one hole will form, and what eventually happens is there are the several holes sort of form like this, and the dynamics or the evolution of the surface does not stop at the stage of hole formation only, and there is subsequent morphological evolution and dwetting of the film. Okay. So, there are essentially two aspects to thin film instability or the spontaneous instability of a thin film. The first thing is that you initially start off or take a continuous thin film which spontaneously ruptures, and the second aspect is this ruptured film subsequently evolves. So, there is some additional reorganization within this ruptured film which eventually results in the final dwetted morphology. So, there are essentially two specific or different parts of the whole process of instability and dwetting of a polymer thin film. So, if you look at the title of the module, I have deliberately kept it as instability and dwetting of the polymer thin film. Okay. So, essentially if we look into this film, so first part is the manifestation of instability, and second part is the dwetting of an unstable, one can also say ruptured film. What we have discussed so far qualitatively is the manifestation of the spontaneous instability, which you may just want to note down that this mode of spontaneous instability is often referred to as the Spinodal instability. Which has its sort of similarity or the origin in fluid mixtures where the spinodal decomposition in fluid mixtures where there is a fluctuation in the composition. You can just do a internet search to find out what exactly spinodal decomposition means, but this is since it's these fluctuations you have at the interface which eventually results in this spontaneous form of instability, these are often referred to as the spinodal instability. What we do now in the remaining part of this particular class is we do a quick mathematical treatment of this manifestation of instability and try to figure out what exactly or how exactly the system becomes unstable, and more importantly mathematically how you can distinguish between a stable, unstable and a metastable film. But before we do that, I would like to give you or show you a real time movie in which you can actually see. So, this is a movie that has been taken in my lab by my research students, where you can see. So, this is what you are seeing is under an optical microscope a real time picture, and all you see that you have taken this gray color is actually an intact thin film, and you see that there are some holes which have just started to appear. Okay. So, these holes you now understand has appeared due to spinodal instability. So, this was a spinodally unstable film. These holes have just started to appear. So, we have taken a polystyrene film. It is a very common model system. We will talk in greater detail about dwetting experiments. So, this film, the thickness was grossly of the order of 25 nanometer. Which was created by spin coating from a solution, a very dilute solution in toluene. Concentration lies between 0.5% weight by volume. Typically 100 microliter solution is dispensed. We have talked about spin coating in greater detail. So, each one of these parameters should make sense to you. 100 microliter solution is dispensed, and then typically you rotate at an RPM, rotate for 1 minute at an RPM of 2500 to get these type of 25 nanometer thick film. Just would like to highlight the substrate used was a silicon wafer. Coated with native oxide layer, thickness of which is 1.5 nanometer. So, once this film has been coated, then the solvent evaporates. These are long chain polystyrene molecules. The molecular weight is around 280 K. So, they are highly long chain molecule in an entangled state. So, at room temperature they behave more like a amorphous solid film. So, you do not, irrespective of whether the film is thermodynamically stable or not, which we have not distinguished or talked in greater detail as of now, but what you can understand that whether the film has been sprayed on a wettable surface or not, irrespective of that, this film remains intact at room temperature. Okay. So, at room temperature, the film remains intact. Now, in order to manifest the dwetting, or in order to trigger the dwetting, what is typically done is that the film is heated beyond its glass transition temperature. So, once the film then there is a significant drop in the viscosity, and then depending on the attractive interaction forces, let us say this fluctuations can amplify. At a temperature lower than the glass transition temperature, the material is too stiff, so that these fluctuations do not manifest. It behaves more like a solid. So, irrespective of its thermodynamic stability, the film is or the system is kinetically stabilized. So, nothing happens. One can look into the Deborah's number, essentially, which talks about the time scales, and at room temperature the system might eventually become unstable, because it is a thermodynamically unstable. It remains a thermodynamically unstable system, but it is going to take infinite time. However, once the film is now heated beyond glass transition temperature and the viscosity has dropped, so what happens is that the film is now more in a liquid form. So, these fluctuations now manifest at the surface, and now depending on the interfacial interaction, nature of the interfacial interaction, the liquid air interface or the film air interface, that is this interface, is now in a position to deform, or the attraction. Or this interface can now deform to these interfacial the magnitude of the interfacial forces, because while talking about the AFM, we also picked up cantilevers which were soft enough so that they deformed due to the interfacial forces. So, essentially here also the same thing happens. Now, once the film is in a liquid form, so they start deforming to the interfacial forces, and then the fluctuations can amplify and grow. So, what you are seeing now on the computer screen is a scenario where the film has just ruptured and the holes have just started to appear. So, once you heat it further, you are now in that you see the holes are growing, and there is some additional dynamics that is occurring over here. So, these holes grow, and eventually it results in some isolated droplets. One can see, so this is the video you just saw, where it is in a little smaller size now. You have these holes which are appearing, then the holes grow, and eventually at the late stage they form some isolated drops. You can see at a higher magnification what happens at the late stage. So, you see some polymer ribbon like structures, and then these ribbons eventually break down. These ribbons becomes unstable and they break down, forming random isolated polymer drops. Okay. So, this late stage breaking down of the ribbons are attributed to a form of instability which is very well known, and which we have already covered. I will show you this video again, which we have already covered as a part of this course, and it is nothing other than the Rayleigh instability. So, essentially we have some very thin threads of polymer which now disintegrate due to Rayleigh instability, resulting in final dwetted droplets. So, now what you have seen, you have actually had a first hand look under a real time microscope. Maybe the dynamics can be a little slower depending on the molecular weight, but which might have been a little bit exaggerated. So, let us have a quick look at both the movies again. So, here is it. You have some isolated holes appearing due to the mechanism we have talked here. I will repeat. So, here you see the holes, the appearance of the holes is due to amplification of thermally excited capillary waves due to attractive interfacial interaction. Okay. And so, you have seen that the holes have just appeared, and then the subsequent section is the growth of the holes and dwetting of the film on the substrate, which we have not yet talked so far and which we will take up in a subsequent class. But you can just have a quick look at what happens. So, the holes grow, and then there can be different morphologies depending on a various host of parameters. So, on the right hand side of the screen you have the whole sequence of a film dewetting, the different stages which are written. So, the first two should make sense to you as of now, because the first one is the formation of these undulations, which is the capillary wave we are talking about, and that the thermally excited capillary waves, and in the event that they are amplified because of attractive interfacial interaction, it results in the formation of holes. The subsequent four stages are also very common, but I think we will discuss it at a subsequent class when we talk in greater detail about the different stages associated with dewetting. Okay, and here is another again a quick look at what happens at the late stage. So, this is interesting. You have at a stage, at an intermediate stage, and these are all part of this second stage, which we have not yet discussed, the dewetting sequence. Okay, so dewetting sequence is yet to be discussed. This is a part of dewetting sequence. Towards the later stages, these polymer threads sort of break into isolated droplets due to Rayleigh instability. So, this part we will take up later, but let us now try to quantify mathematically how a film becomes unstable, or what are the conditions under which a film becomes unstable, and a thin film becomes spontaneously unstable. And based on that, we try to distinguish a stable, unstable, and a metastable film. So, the background information or the background equations that we may want to have is that we have a incompressible. So, or in other words, let us start it with fluid as a continuum is still valid, though we are talking about a very thin film. The second thing is the continuity equation for a incompressible fluid is valid, which takes the form we assume that the flow is extremely wide. So, this is my coordinate system, this is our coordinate system, this is x and this is z. We assume that the system stretches to infinity in the y direction, and therefore, all the derivatives with there is no variation of the flow properties in y direction. So, essentially we are talking about a two-dimensional flow. We further assume, which can be sort of a little bit of counterintuitive, assuming the fact that we are talking about a polymer, we assume a Newtonian fluid, and it turns out that the assumption works rather well. Newtonian fluid, and the governing equations are the Navier-Stokes equation incorporating the effect of interfacial interaction. So, we essentially incorporate phi, which is del g del x, and is phi is known as the effective interface potential. This effect is included in the respective components. Of the Navier-Stokes equation. So, the equations essentially take the form of, so this is my equation, this is our equation of continuity, which is then we have a scenario like the x component Navier-Stokes is the standard Navier-Stokes equation for a 2D system. This is the only additional term where we incorporate the influence of the interfacial interaction in the form of considering the phi. We will come to the expression of phi, but for the time being you just understand that phi bears the signature of the interfacial interaction, something which is absent in a macroscopic flow, and therefore we never consider it. And the z component Okay. So, these are the essentially the three equations which we will be using. One can one can write it as more in the cyclic form. Nothing was wrong in the way I wrote it, but maybe you just wanted to have it in this form. In addition, so this is my equation of continuity, this is my x component Navier-Stokes equation, this is my z component Navier-Stokes equation. In addition to these, there are certain additional equations which are active in the background. The first thing is that though we assume a film, a flat film, we understand that the top surface is not flat. This is important. So, the moment the top surface is not flat, there is the pressure is not uniform at the outside and inside of the film. So, if this is exposed to atmosphere, you can't say that the entire film surface, the first layer inside the liquid layer, is at P atmosphere. Instead, you have spatial variation of Laplace pressure because of the curvature effect or the non-flatness of the film surface. Okay. So, consequently what we have is that the Young Laplace equation is valid on the surface. And the other thing, we assume that we regard these undulations to be axisymmetric. Okay. So, the surface undulations and consequently the form of Young Laplace equation that can be used is this one. We have already done this derivation. So, refer to your previous class notes or refer to some of the previous lectures for detailed derivation of this. In within the I think the first 7 or 8 lectures itself, we did this detailed derivation considering the Helmholtz free energy, which leads to our essential motivation was to find out the geometry of the surface which corresponds to a minimum thermodynamic energy criteria. And the same thing is valid also here. Yesterday or the previous few lectures, we have talked about the sign of delta G, and we have argued that two surfaces or a film will rupture depending on the scenario where delta G becomes negative, or sort of a ruptured film results or leads to further reduction of the energy. So, the basic motivation based on which we did this derivation and based on which a spontaneous a intact thin film becomes spontaneously unstable, they are same. Both have the same motivation of energy minimization. Now, what this equation gives you, or if you look at how we derived it, it gives you that H, or which is the film thickness, is H. So, what it implies that H is not uniform, and H is a function of x. Okay. Now, what we can do here, we can regard that the amplitude or the wavelength of the instability is much larger than the film thickness. Which implies that del H del x is nearly equal to 0. Okay. So, it is like this, it is much larger as compared to the film thickness. So, del H del x is equal to 0. This is what is known as the long wave instability. So, if you now plug in the condition of long wave instability, okay, let me just remind this H x in this equation implies del H del x, H x x refers to del 2 H del x square and so on. So, if we now plug in the condition of long wave instability into the Young-Laplace equation, or the expression for Young-Laplace equation for an axis symmetric surface, we get a very neat expression for Young-Laplace equation, which is delta p into gamma times H x x. Now, please do not confuse yourself with the fact that if H x is equal to 0, so this implies that H x is equal to 0. Please do not confuse yourself with the fact that if H x is equal to 0, H x x also has to be 0. You just refer to your basic fundamentals about optimization or maximum minimum. What you do, you have a function y equal to f x. The necessary condition for finding the minima or the optima is you set f dash x is equal to 0, and then evaluate that x, and then you find out, what you typically do is you find out the sign of f double dash x. So, check out whether it is positive or negative, and based on that you tell whether it is a minima or maxima. So, there is a huge set of problems where you have already encountered that at a specific x, f dash x is equal to 0, but f double dash x is not equal to 0. While teaching in the class, I have often encountered this question from students that well sir, h x is equal to 0, then one should also set h double dash x is equal to 0, and immediately one gets that delta p should be equal to 0, which essentially implies that you are now looking at a perfectly flat interface, which is not the case. So, please do not confuse. the condition of long wave instability, which in otherwise in simple words means that the wavelength of the instability is much higher as compared to the film thickness, results in sort of a very sort of an relaxed slopes or curvature of the film surface, which means that del H del x is equal to 0, and you plug it in to get this form of the Young Laplace equation. So, along with the 3 governing equations which we have listed in this, these are the 3 governing equations, we have a 4th equation which we will be needing to use. Okay. Now, the other condition we need to look at is that since the liquid air interface is no longer flat, we need to care about the local mass balance at the interface. Or in other words, what it means that this is a flat interface. So, we argued that for a flat interface, the surface, the velocities, the components of the surface velocities will be 0. However, what happens here is that you have an interface which is no longer flat. This means that there are US and WS Okay. These are the components of surface velocity or components of they become non-zero or they exist. Okay. So, we have to worry about some sort of a local mass balance at the interface, or in other words, we need to worry about a mechanism to that provides a functionality between US and WS. Okay. So, for that we consider a mass balance about the shaded area. Let us say this is the local height of the film, which is h. This is Ws. So, if we just calculate the rate of accumulation, what we can find out is del t into h dx. Of course, the density remains constant, is integral 0 to h u dz at x minus integral 0 to h u dz at x plus dx. Okay. So, this integral refers to the amount of liquid that is entering from this phase for the entire height 0 to h, and this refers to the amount of liquid that is leaving or entering. Do not be worried about whether it is leaving or entering, because the appropriate sign of u will be there to take care of it. So, I will just quickly redraw this figure. So, the rate of accumulation is del del t into h dx. Of course, we assume that it stretches in the infinity in the y direction. Okay. So, taking the limit of dx tending to 0, we essentially get to the equation h itself is a function of x and t. So, this is essentially we need to apply to evaluate this integral. This is your first year mathematics. We need to, this is essentially the differentiation of an integral, as you can see. As you can see, and you need to apply the Leibniz rule. For differentiation of an integral, and what we have that if phi y is equal to del phi del y is given as f b y into d dy of b y minus f a y into d dy of a y plus you can look at any standard mathematics textbook like Kreyszig or whatever to find out this. Okay. So, this is the Leibniz rule. If you apply this, what you get, and this is our equation. So, if you apply this, we will get f b y here is u at h, which we are terming as u s. F a y here is u at h equal to 0, that is at the bottom surface, which is 0 due to no slip boundary condition. Okay. And b y is nothing but the film thickness actually in our case. So, this term remains, this term vanishes, and this term essentially takes the shape integral of a is 0, b is h, f is essentially u here, del u del x into del z in our setting. So, if you do that carefully into this equation, then what you get in the final form is that del h del t plus integral 0 to h del u del x into del z plus us del h del x is equal to 0. So, this is simple. You just have to plug in, do this integral, assuming or understanding that here your f is u and x is z. So, you just do the integration, plug it in into the Leibniz rule, and I have also written the individual terms which will come in. So, just check it out if you can do it yourself, and finally, you will get to this expression. Now, from continuity, we have del u del x plus del w del z is equal to 0, considering that there is no variation in the y direction. Therefore, what comes out is del u del x is equal to minus del w del z. You substitute this expression of del u del x over here to get from this equation, you get or you can write it, therefore, integral of del u del x into del z evaluated between 0 and h turns out to be minus integral of del w del z evaluated between 0 and h, and this turns out to be minus w evaluated at z is equal to 0 and z is equal to h. Okay, so, this is the film. So, this is z is equal to 0 and you are talking about w is equal to 0 at z is equal to 0, because of the fact, this is not because of no slip, but this is because of the fact that you have a solid substrate, solid impermeable substrate. Okay. And therefore, this term tends to 0, and w at h, that is over here, is nothing but ws. So, the second term leads to minus ws. So, if you substitute that, you eventually have the expression of the equation as del h del t minus ws plus us del h del x is equal to 0, or if you reorganize, del h del t plus us del h del x is equal to ws. So, here is an equation that sort of now you can see bridges or combines the us and ws. So, this is the fifth equation we will be needing to evaluate our system or understand the dynamics of our system. So, I will just do a quick recap before proceeding further. So, we are now looking at the mathematical formulation of the condition under which a thin film can become unstable. So, we have taken a thin film like this and we have argued that there is no variation in the y direction. So, the film is coated on top of a solid surface, and what we have, the fluid as a continuum is valid. Continuity equation for 2D flow neglecting the variation in y direction and for an incompressible fluid is this. It is a Newtonian fluid, and in the Navier-Stokes equation remains the governing equation. We have incorporated the effect of the effective interface potential, which gives us the equation of continuity and the x and y component, x and z components Navier-Stokes equation like this. Then since we have a surface which is no longer perfectly flat, therefore, we assume that the surface is undulated. Therefore, there is a variation of Laplace pressure, which we have therefore, we have considered the Young Laplace equation. Only thing we have considered that the undulations are axis symmetric. Therefore, this form of Young Laplace equation we can use. Into that, we have now assumed that the nature of the instability is long wave, which makes del H del x is equal to 0. So, we have plugged in the long wave the condition for the long wave instability has been plugged in here, and which gives to this form of the Young Laplace equation. And finally, since we understand that the flat top surface is not flat, we were looking for an equation that sort of combines the influence of the surface components, the components of velocity at the surface, that is us and ws, which we have done by based on sort of a local mass balance. And for that, in order to get to that equation, we had to invoke the Leibniz rule for differentiation of an integral, and eventually that has given us, with appropriate manipulation, little bit of very simple algebraic manipulation, which I am sure if you look carefully and try it couple of times, you will be able to do it yourself, gets to this equation, which is known as the kinematic boundary condition. Our next lecture, we will start our discussion from these set of governing equations and see, based on a linear stability analysis, how we can identify or distinguish a film which is stable, unstable, and metastable. Thank you.